Hello, welcome back to Z Mathematics. Today we are starting Corpuscle 2 complex numbers. The first half of this is lovely. The second half, when it gets to the sums of series and stuff like that, is like, don't even get me started. But I've been requested to do it. It will get me good practice as well, so let's just get into it. So, the chapter starts off with defining Euler's relation or Euler's formula, and I guess we could prove it, but it uses the Maclaurin series, and Maclaurin series is, I think, the next chapter, chapter 2, which is part of series. So if you haven't gone ahead, if you're going in order, you will not understand the proof for it just yet, but I can basically just quickly run through it. So in chapter 2 of Corpuscle 2, we learn about the Maclaurin series. And what the Maclaurin series does is it allows us to take a function like sine x, cos x, ln of 1 minus x, and it allows us to express that function as an infinite polynomial. If you're going in order of the textbook, then you'll learn this in the next chapter. But basically, we learn that we can expand cos, sine, and e to the x. So, what we learn is that cos x can be represented as the polynomial 1 minus x squared over 2 factorial, added to x to the power of 4 over 4 factorial, minus x to the power of 6 over 6 factorial, plus x to the power of 8 over 8 factorial, minus ... So we see that there's this alternating plus minus plus minus. We start off with positive 1, then minus, plus, minus, and it will keep going plus minus forever. And we also see that the powers of x are increasing, and they're increasing evenly in the even numbers. So technically this is the x to the power of 0. Then we have 2, 4, 6, 8, then it'll carry on 10, 12, 14, 16, blah blah blah. So this is the expansion for cos x. For sin x, we basically have the opposite term. So we start with x, then we have minus x cubed over 3 factorial, and this is just the odd numbers. There's still this alternating plus minus, so then we get plus x to the power of 5 over 5 factorial, minus x to the power of 7 over 7 factorial, plus x to the power of 9 over 9 factorial, minus ... So these just keep going on forever and ever. Now we also learn the expansion for e to the x. E to the x is easy. It's got every single term and they're all positive. So we have 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the power of 4 over 4 factorial, and so on. So we can basically see that whatever cos x is missing, like any x terms or x cubed terms or whatever, sin x has. And then e to the x just has everything. But the difference is that these are all positive terms, they've got plus everywhere, whereas these have an alternating plus minus. And what Euler found is that if we do an expansion for e to the power of I multiplied by x, we find something very cool. What do we know about I and its powers? Well, I is just I. I squared is minus 1. I cubed is minus I. I to the power of 4 is 1. Then I to the power of 5 is just I again. So we're just going back in this loop, and then we'll go to minus 1 again, then we'll just go down. So when we have the powers of I, they can change the signs because we'll get minus 1 and 1 sometimes. So if we do e to the ix now, we'll just plug in ix wherever there's a single x. So this stays as 1, then we're going to get plus ix, then we're going to get plus ix squared over 2 factorial, plus ix cubed over 3 factorial, plus ix to the power of 4 over 4 factorial, and so on. Now what this gives us is 1 plus ix. Now ix all squared is I squared x squared. Well, I squared is minus 1, so we get minus x squared over 2 factorial. I cubed is minus I, so here we get minus ix cubed over 3 factorial. I to the power of 4 is 1, so here we just get plus x to the power of 4 over 4 factorial. The next term we get ix to the power of 5 over 5 factorial. Then the next term we get minus x to the power of 6 over 6 factorial, and so on. So we see that some terms contain an I, and some terms don't. And we see this plus, plus, minus, minus, plus, plus, minus. Okay, this should be a minus. But we see this pattern. Now, what we can do is we can just group all the real parts and group all the imaginary parts. So all the terms that are like free of an I, that don't contain an I, so 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial, we can just group them as like one kind of group. And then ix minus ix cubed over 3 factorial, and so on, we can group that as like the imaginary part. So what we can say is that e to the ix is the real part of e to the ix added to the imaginary part of e to the ix. Because we're not subtracting or like removing any terms, we're just rearranging them. So the real part of e to the ix is 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial, and so on. Now the imaginary part, because they all contain an I, we can just factor that out. So if we factor out the I, what we're left with is x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial, and so on. Now what do we notice? This is exactly the same as this. This is exactly the same as this. So we can do some substitution now. The real part of e to the ix is literally just cos x. And then here we've got this plus I lots of sin x. And this is all equal to e to the ix. So we have proved Euler's identity, or Euler's formula. E to the ix is equal to cos x plus I sin x. How cool is that? So, this is what we've got over here. E to the ix is equal to cos x plus I sin x, and it's Euler's relation or Euler's formula. So yeah. So basically here, that's what we've just defined. And of course, x is just a variable, so here you could have, I don't know, w or y or theta. So, a general complex number, z, is x plus iy. We know that can be represented in the form r cos theta plus I sin theta, but r is your modulus and theta is your argument, so that's over here. Well, we just defined this to be e to the ix, but here we've got theta, so we have a theta. So all this becomes is we have the r over here, and then we just have e to the I theta. So now, let's try this textbook example. So we want to express this complex number in the form r e to the I theta. How do we do this? Well, we know that we want to express it in the form r e to the I theta. Well, what is r? R is the modulus, so r, we know, is just the square root of 2 squared plus 3 squared. And that's the square root of 13. Now what's theta? Well, if we sketch z on real imaginary, 2 minus 3i. 2 minus 3i. Here we go. So our argument is negative theta. So theta is just going to be minus arctan of 3 over 2. And to 3 significant figures, this is negative 0.983. Well, therefore, we can say that z is r e to the I theta, which is root 13, e to the I minus 0.983. Yeah, I guess you can tidy that up to get root 13 e to the minus 0.983i. And that's z expressed in polar form. Now I've got the answer here. So you can check this and we get the same thing. Correct. So, that's the first part of the chapter done. It's just being able to convert from like Cartesian or your x plus iy to polar form. Now, in the next bit of the chapter, we take it further into multiplying and dividing the complex numbers. And you'll see we get things like this, which are like, what the hell? All it is just converting to polar, and that just makes things so much easier because you just deal with indices. Now, there are some things over here. So if you have two complex numbers multiplied together, all you do is you multiply their two moduli and add their two arguments. And then it's the opposite for if you're dividing them. If you're dividing two complex numbers, you divide the moduli and then you subtract the arguments. Now this is, see, if you've got r1 e to the I theta, r2 e to the I theta, if you're multiplying together you'll get r1, r2, and then you just add the indices together, so you're going to get or if this theta 1, theta 2, you'll get theta 1 plus theta 2. Basically I've just proved it now. And then you just do the opposite for that. So, we want to express this in the form r e to the I theta. Well, let's just convert everything in that form. So, we know it's in the form r cos theta plus I sine theta. Well, we see that r is 2 and theta is pi by 12. So, in r e to the I theta, that's just going to be 2e to the I pi by 12. So that's our complex number on top. And on the bottom, we're going to have root 2 e to the 5 pi I over 6. Well, now we've got z1 over z2, so that's just this. Divide the moduli, subtract the arguments. Divide the moduli, we're going to get 2 over root 2, which is 2 root 2 over 2, which just becomes root 2. And then we're going to do I pi by 12 minus 5 pi I by 6. So on your calculator you can just do pi by 12 minus 5 pi by 6. So pi, so adding the I, you're just going to get e to the minus 3i pi over 4. And there you go. Now we've also got an answer to this. Yep. Root 2 e to the minus 3 pi I over 4. So, that's that part of the chapter done. Next part, de Moivre's theorem. This is such a good theorem, and it's really good for like things like this to get really good identities. So, de Moivre's theorem. That basically says if you take complex number z, so r cos theta plus I sine theta, and you raise it all to the power of n, that becomes r to the power of n, and n multiplied by your theta or your argument. And that's where n is an integer. Now you can prove this by induction. In the book it tells you how to prove it by induction by doing your base step, assumption, inductive step, and your conclusion. So you can look at that, but it should be simple. You just plug in 1 for n, then you just assume true for k, then prove it true for k plus 1. It's simple. So that's what I've mentioned here. You can prove it by induction for n as a positive integer. So we can use this theorem to simplify things like this. So cos of 9 pi by 17 plus I sine 9 pi by 17 all raised to the power of 5. Well, let's use de Moivre's theorem. Well, here we can say that r is 1. Oops, r is 1 because there's nothing in front of the brackets. So r to the power of n, which is going to be r to the power of 5, is just going to be 1 to the power of 5, which is this 1. So there'll be nothing in front still. But now we multiply theta by n. So we're going to get cos of 9 pi by 17 times 5, which is 45 pi by 17, added to I sine 45 pi by 17. And this is going to be all over. Right, here we've got a minus. Now we know for things like this, we know that cos of minus theta is just cos theta, because it's an even function, and sine of minus theta is minus sine theta. So this minus sine theta is just sine of minus theta. So the argument here is minus 2 pi by 17. Because if we plug that into theta, it's going to make no difference here. We'll still get cos of 2 pi by 17, but here we'll get minus I sine of 2 pi by 17. So here theta is minus 2 pi by 17. Be careful. So what we can do is, again, write it in, use de Moivre's theorem. So what we're going to do is cos of minus 2 pi by 17 times 3. So that's going to be minus 6 pi by 17. minus I sine, actually it's going to be plus I sine, of minus 6 pi by 17. Now we've got z1 over z2, so we divide the moduli, well that's just going to still be 1, and then all we do is subtract the arguments. So, or if you want, we could just convert this to re to the I theta, so we're going to get e to the 45 I pi over 17, all over e to the minus 6 pi by 17. So now we can literally just say, we just subtract the arguments, so we're going to get e, and then 45 pi by 17 minus 6 pi by 17. And this gives us 3 pi. So that's just going to give us 3i pi. Is that our final answer? Not really. We know that, actually I should have just left it in cos and sine form, but we know that this is just cos of 3 pi plus I sine of 3 pi. Now what are multiples of pi for sine and cos? We know that cos of pi is minus 1. So multiples of pi will give minus 1. So here we're just getting minus 1. And then multiples of pi for sine just give us 0. So we're just going to get I times 0, which is 0. So our answer is minus 1. And this is also Euler's formula. And this is also Euler's formula, which is e to the I pi plus 1 equals 0. And it relates like 5 of the most fundamental constants, like 5 really like cool constants. You've got e, I, pi, 1 and 0, and they're all related in this formula, because e to the I pi is cos of pi plus I sine of pi, which is minus 1 plus 0, which is minus 1, and then you have this plus 1 to make 0. So it's really cool because it basically links trig, exponentials, and just normal numbers together, so it's really cool. Answer? Minus 1. All good. Okay. Now we can extend the Moivre's theorem into trig identities.